So all we're going to do is put into the notes today. And so if you don't have the note guide, it's fine. And it won't be flipping sideways on you like this. We're going to put our sine and cosine parent function in. So you guys already have that classwork handout that like has the function for you. But we're not going to use all of the points. So the first thing I want you guys to remember is that the amplitude was 1. So if I get to choose to label my graph and I don't have a change in amplitude, I'm labeling my y-axis with like 1 and -1. And then remember that the x's were angles that we were plugging in. So the x's are going to be maybe a little stranger than like you're used to plugging in. We want to go 1 lap around the unit circle. So we want to go from 0 to 2 pi. Okay? And so point-wise, we want 0 to be the first thing that we look at plugging in and 2 pi to be back at the beginning. And then we've made the parent function a couple times and looked at it a couple ways. Remember, we tried to pick the easiest values from the unit circle. And so the easiest sine values for us to graph would be anytime it turns out to be 0 or 1 or -1. So we tried to pick every like 90 degrees on the unit circle. Okay, but when we graph traditionally in math, we use radians for the x-axis, so just be prepared that you're seeing that and not degrees. So every 90 degrees really means every pi over 2 for us. So it's like counting by halves. Okay, like we have 0, 1/2 pi, 2 halves, which is a pi, 3 halves pi, and then like 4 halves, which is 2. Those are what I want to label on the graph. This graph has more tick marks than that, so it's kind of going to be every other tick mark. Oops. Okay. And then we're just going to go ahead and fill in the points. Now remember, if you were building the parent function on like a test or something and you couldn't remember what values you wanted, just use a different message. Yeah. If you couldn't remember what values you wanted, you could use your unit circle because you'll have that with you. So like if you go to an angle of 0, what is the sine at 0? That's going to give you the y-coordinate for our graph. So the sine at 0 is 0. At pi over 2, it was 1. Then it went back to 0, then -1, and then 0. So you may memorize this. You may have to use your unit circle every time. It depends on you. And then I'm going to plot those points on here. And that's our sine parent function. So if you're a visual person, and your issue with sine and cosine is that they both kind of look the same, try to look at how one sequence or one period of the wave looks. The sine starts at 0, goes up, and then down and ends back at 0. Okay? The cosine is going to look slightly different. All right, so the period is 2 pi. That's how long it takes us to get through one cycle. So that's something we're going to want to know about the parent function. Just like with log and exponential graphs, you like knew where the parent function's asymptote was. You want to know the period for the sine and cosine functions. And then the frequency is just always the reciprocal of that. We're just getting you guys used to that relationship because it will help a lot in your project. Okay. Yep.
On quiz, will be asked like the period of frequency.
Yes. And I'm going to write it like this so that you guys understand the pi is in the denominator with the 2. And then the amplitude is 1. Okay. And then you can make any other notes for yourself that you want to help you remember this is the sine function versus the cosine graph, even though they're going to look really, really similar. Okay. Any questions about the parent part of it? So again, we've seen it a couple times. You guys saw it on Desmos. You guys plugged in some numbers and made a graph of it on that classwork handout. This is the simplest and least amount of points you would need to create for yourself a sine function. And if you want to transform them, you don't want to transform like 10 points. You'd rather transform 5. Okay? And then you can use the pattern after that. And then we're going to do the same thing for cosine. So you've seen cosine and sine and that they have a lot of similar things. The similar things they have is that they have the same period and the same amplitude, which means they also have the same frequency. Okay? And given that they have that same period, we want an amplitude, we want the same kind of labels on our graph. Okay? So we want to look at one cycle of the sine wave going from 0 to 2 pi. So everything I'm about to do is going to seem exactly like the sine function. The only thing that's different is where the points end up. Okay? So again, I wanted to go every 90 degrees, which is like a half a pi. So it looks like I'm numbering by halves here. The difference is I'm going to plot the cosine value at each of those angles. So like the cosine at 0 is 1, and then it's 0 at pi over 2, and then it's -1, and then it's 0, and then it's 1. So again, try and find a way to memorize. Just memorizing them and having no context is probably a little hard because they're so similar. You have to find a way to tell them apart. So the cosine graph, if we look, let me label my axis again. So I'm going to put pi over 2, pi, and 3 pi over 2. Okay. And then I'm going to plot these points at the appropriate places. Okay. And then I know it's a curve, so I know it's supposed to go like that and then continue. So your job is going to be to kind of decipher the sine and cosine. Everything else about them is going to be the same. The way we figure out the period, the amplitude, the way we do the transformations. So something that you might struggle with, so just figure out a way to help yourself here, is making these parent functions because they're just slightly different. Okay? So find something that really helps you identify sine versus cosine. Okay? For me, it's that sine starts at that 0, 0 spot. Okay, versus the cosine, I look for a starting point that's at the peak. Okay, so that's kind of what I look for. You don't have to look for the same thing. Just throwing it out there. We'll do the tangent at a different time. Okay. Make sure you guys get your cosine graphs in the middle. Any questions while people are finishing up getting their like cosine graphs and sine graphs on their paper? Okay, so good news and bad news as we look at the example. So the good news is the transformations work the same way they always have. A vertical stretch is a vertical stretch. A horizontal compression will be a horizontal compression. Reflections, all of those things. And you can still just use the chart like you did before and just convert it over. What you're not going to like about that process is look at the x values of your chart, okay? So you have to be a little bit patient with yourself or patient with me if like that's where your anger goes to, if you have to deal a lot with fractions. In the fact that you're going to have to deal with things that have pi in them and then maybe compress them and add things to them. So you're going to be doing fraction math and you're going to do it with fractions that might have a pi value in them because that's a common radian thing that we're using. But otherwise the process is going to be the same as what you've always done. So we're going to look at this example. Okay. So I tried to split it up for you guys so that we can kind of review all the things that we've done before. We're doing them here. So the first thing we want to do is we always want to write our function in that format where like the b value is separate from the x minus h quantity. So like right here, we want that b still inside of the cosine but separate from x minus h. Otherwise, we don't really know how much left and right we've shifted it, right? We've only studied things if they're written in this exact format. So we want to change that every time. In this equation, there isn't anything being added or subtracted from x, so you basically already have it, okay? So there's not really anything here to rewrite. Our a is a -1, our b is a 3. We don't have an h value, it's 0, and our k is 1. Is that okay with everybody? So it's kind of in that format. And if you didn't get what I just said, I'm identifying like a is -1, b is 3, h is 0, and k is 1. If those are the values, if you like to look at them that way to help you with your transformations, okay? So then what we want to be able to do is our second step is going to be to get points, and then thirdly, we're going to graph it. While you're getting those points, though, when you go to graph it, things you should also know is you should be able to list the characteristics in the transformations, okay? So I'm going to list the transformations as we make the table because I feel like they go hand in hand. So first I'm going to put my parent function. Remember, this is something I have to have memorized, or I can quickly figure it out with my unit circle being the only tool because that's all I'm going to have. Since this is a cosine graph, so my parent function is the basic cosine graph. We just did it. It looks like this. So for me personally, I do have memorized that for sine and cosine, they have a period of 2 pi if they haven't been stretched or compressed. So I want the parent to go from 0 to 2 pi. And I know that we went around at every 90 degrees. So that's kind of how I know which angles to include in here. And again, I have that picture in my head of the sine starting at 0, 0 and going up and then down. So I know that it starts at 0, goes up, back to 0, then down and back to 0 for its y values. If you didn't know that, you have your unit circle. You could go to each of those angles and look at what the sine value would be at those angles to get the y coordinates. Okay? And then we're going to make our transformed table, and kind of as we do that, I'm going to list our transformations, like I said, because I think they go hand in hand. Whatever arithmetic I'm going to do right here to change the numbers in this chart, I can say in words as a transformation. So A was -1. Is that going to affect our x values or our y values? Our y values, okay? It's not inside the parentheses affecting x, it's going to affect y. So all of the y's are going to have their opposite taken based on that negative that showed up in the a value. In words, what kind of transformation is this? Good, this is a reflection. Anytime you're multiplying by a negative, it's a reflection. And because we're changing y's, and y's would go from up to down or down to up, that is flipping them over the x-axis. Okay? All right, the b value is 3. Is a b value going to affect the x or y values in our chart? X, because it's in there happening to x. And how exactly does that b value of 3 really play into our distances on the graph? Do we times x by 3? Aaron? 1/3. Good, we use the reciprocal. So if we're really timesing the old distances by 1/3, what are we doing to those distances? Are we making them bigger or smaller? Smaller, so we're compressing them, right? So it's happening to x, so it's horizontal, and it's making the distances smaller than they were before, so that's a compression of that distance. Okay? We have no h value, so I'm not going to be shifting anything left or right. And then we have a k value of 1. Is that going to affect my x values or my y values? Y. Okay. And what type of transformation is that in words? We're shifting our graph up 1. Okay. Okay. And so now we're going to do what we would normally do, just with a little bit of annoying values in the x. Okay. And we're going to go through and transfer all of these. So I'm going to take everything that was in x. 0 is going to get multiplied by 1/3. Pi over 2 is going to get multiplied by 1/3. Pi is going to get multiplied by 1/3. 3 pi over 2 is going to get multiplied by 1/3. And 2 pi is going to get multiplied by 1/3. That's how I'm making my new x's, right? So I wrote it out visually because I know you guys aren't super fans of fractions. So I wrote it out so we can see. So 0 times 1/3 is going to give us 0. Pi over 2 times 1/3. Remember, you multiply fractions straight across. So pi times 1 will still be pi. 2 times 3 will be 6. So I get pi over 6, which you might think is horrible, but really pi over 6 is just 30 degrees on our unit circle. Okay, it's not as bad as it looks, right? So that became pi over 6. So pi times 1/3 will be pi over 3. Here the 3's will cancel because they have a common factor in the numerator and denominator, so that will give us pi over 2. And then 2 pi times 1/3 will give us 2 pi over 3. Okay? And then you can take all the y values, take their opposite, and add 1 to them. I think you guys are a little more familiar with that, so I'm not going to write those ones out as much. So then here's what we have. Yeah, Aaron. Oh, yeah, it is. You guys, I suck. I totally was doing sine. I did exactly what I told you guys not to do. Do you guys know the mistake that I just made? Okay, so everybody fix it right now. And it's for the whole world because it's being recorded. Good job, Aaron. You would have just like ruined everybody's notes if nobody said anything. So do 1, 0, -1, 0. I apologize. It's not because I don't know. It's that normally my first example is sine. So I was doing sine, and I'm just going to change these y values to those. And then I'm going to address it one more time because I want to make sure you guys know what I did. Did everybody see what I did? So I was graphing the wrong function, right? I was graphing our equation like it was a sine equation, but it's a cosine. I need to pay more attention to what I'm doing. I wrote it and I didn't pay attention to it. So is everybody good about why I changed that? So it should have started at 1 at the highest peak for the parent because it was that cosine, and it wasn't that sine function. So is everybody fixed on your paper? Is okay? All right. Aaron, like superstar. You're on the wall for sure. Yeah, that's true, in place of Mo. Okay. All right, so normally this is pretty simple, and then we just take it straight to the graph, and we just like start numbering things and graphing them. These values in this column for x are going to make it a little bit hard for us to graph sometimes, because here's the thing, like, what should I number by? So what you guys have right here is actually the nicest situation, because it has a list of numbers for you that includes 0. If it includes 0, I actually know what to do, because after 0, I want the next marking to be at pi over 6, and then I want the next marking after that to be at pi over 3, and so it has a list for me in the order I want, but only because it had 0 in it. Do you guys understand that? So like if I took 0 off and it was just a list of numbers, are you allowed to put 0 where you want and then just start your list right after it? If you guys do that, so let's say, I'm just going to off to the side, you guys don't have to write this down, but let's say you guys came up with a list and it says pi over 2, 2 pi over 3, 5 pi over 6, pi, and it keeps going. If you guys went to make this graph and you said, okay, 0, and after 0, I'm going to mark pi over 2, and then 2 pi over 3, and then 5 pi over 6, okay? What is the purpose of the markings on the graph? They're all supposed to be equally spaced apart, right? So like if we just label one thing, we're supposed to know everything on there because it's supposed to be these like consistent markings in a pattern. If you mark pi over 2 right here, how far apart are you saying every mark is? You're saying every time I move over one space on the graph, I'm going a distance of pi over 2. Then what would have come after pi over 2 if every distance is pi over 2? 1 pi over 2 and then 2 pi over 2. Is that what next on my thing? No, but it was next in my list. That's because these numbers exist together somewhere on the number line, but are they the sequence that comes right after 0? Probably not, because that doesn't make sense. Yes.
So it's like the same idea of our like other parent functions, like how we do like 8, 1, 0, 1, 8 kind of thing.
Yeah, and then you'll want to take it to the scale of the graph. So what I really want to know, and I'm going to show you guys this, and we didn't have to use it here because this one starts with 0, so it's really nice. But what you really want to know is how far apart are the points that you're trying to plot. That's how you want to label your graph. Does that make sense to everybody? That I'm supposed to graph these points in order. So what I really want to know is how far apart are these things on the x-axis. Is that okay? So how do I know how far apart two numbers are? How far apart are 10 and 5? 5. How far apart are 10 and 7? 3. How are you doing that in your head quickly? Subtracting. Subtracting tells me how far apart two numbers are, okay? So if 0 wasn't here, what I would do is I would take two numbers from the list and say, I know that 2 pi over 3 comes after pi over 2, but how much is that in between them? And I'd have to actually do a little bit of fraction subtraction. So 2 pi over 3 minus pi over 2. When we subtract fractions, we need to make common denominators, right? Which in this case would be 6. So this is like 4 pi over 6 minus 3 pi over 6, which is pi over 6. If I did it right, every time I do this with any two numbers in this list, I'm going to get pi over 6. It isn't too shabby, right? So I'm going to get pi over 6, okay? And that's how far apart all my markings should be. So the reason I'm telling you this is this will help you scale your graph. What should I number my x-axis by? I should number my x-axis by pi over 6's. And if I do that, I should see this sequence of numbers show up in there because that's how far apart they are. Okay? So when I get to my graph, am going to choose 0. And then as the next number after 0, I'm going to choose pi over 6. Because that's how far apart all my x's are. You guys, if you struggle with what comes after pi over 6, do it like we did when we talk about the 16ths on the ruler and everything like that. If every mark is a pi over 6, you can just literally count by pi over 6's and then go back and reduce them later, right? Meaning my first mark is 1 pi over 6, and the next one would be 2 pi over 6. which then reduces. And then the next one would be 3 pi over 6. And then the next one would be 4 pi over 6, which reduces. And then 5 pi over 6. And then 6 pi over 6. And then 7 pi over 6. And then 8 pi over 6. Okay. Once you have the positive numbers, you can then just reflect them and number it on the negative side as well if you had to. We don't have any points in the negative, but if it got shifted far to the left, we could. Okay. Now, a much easier question. What do you guys want to label the y-axis by? So look back at the numbers for y. Is 1s okay? Yeah, we hit 0, 1, and 2, it looks like, and everything. That's much simpler, right? You just did this for x's, but because x's are numbered in a system that we're just not as familiar with, just didn't look as nice. And now you guys can put on that pattern of points. So our pattern of points, I'm going to zoom out and I'll zoom back in if you guys have to see it so I can see my points at the same time. So we have 0, 1, 0, 0, because I'm not paying attention to my transformed graph. 0, 0, pi over 6, 1, pi over 3, 2, pi over 2, 1, and 2 pi over 3, 0. Now, before I fill in the curve and continue the pattern, first of all, does it look right? So I chose to graph one sequence of a cosine graph. A cosine graph normally looks like a kind of a U thing. This fits it. It's just been flipped upside down. Does it make sense that it was flipped upside down? Because we had the reflection, right? This actually looks just like if the parent was flipped upside down. You can't even see that I compressed it. That's because I cheated and I just changed the numbers here instead of using the regular numbers and trying to make it fit in there. You just renumber your x-axis and be like, oh yeah, look, now it's not 2 pi. Now it's 2 pi over 3 right here. That's how far it goes, okay? So once it looks right, then what you guys can do is you can continue the pattern, okay? So what I see is low point, middle point, high point for the wave. Middle point, low point. The point after this should go back to the middle and then high and then back to the middle and then low. And so I can continue another period of the wave in this direction. I could continue another period in the other direction. And then I would get more of what you guys would expect for your cosine graph. Okay. So we do all our transformations with just one, so it kind of like makes sense and looks right, and then we expand it so we don't have to deal with all those points the whole time. Okay? So same as before, hard part's going to be dealing with the fractions and scaling the x-axis, right?
Like for tests and stuff, do you want us to, or do you expect us to like figure out the pattern and then graph the rest? Like
yes, I'll ask you guys to graph at least 2 periods, which means I won't want just the one that you transformed. I'll want one more in either direction. You guys can decide. I want to see you actually can see the pattern and that it continues on. Okay. All right. So period. The period of this graph. So you can go to your graph and figure it out like we did on Desmos. But here's the thing. You can also do it like you've always done before. What's the normal period of the graph for sine and cosine function, for the parent function? What normally would you write for period? 2 pi. What is the only transformation that changed the wavelength in our investigation? What's the only transformation that made the waves shorter or longer? B, right? And B doesn't work like it says. It says 3 in the equation, and we actually use 1/3. So we would literally just do, just like you transformed all the x's in the equation, take 2 pi, the normal period, and just times it by whatever horizontal stretching or compressing happened. Then my new period is 2 pi over 3. My frequency is just the reciprocal of that, so I'm just going to flip it over. Okay. Amplitude, what is normally the amplitude? 1. Was there any vertical stretching or compressing of this wave? No, so it stays at 1. If there was a vertical stretch or compression, we would multiply it by it. And we never write our amplitude as a negative, okay? It's always just a number. And then phase shift here, did we have any horizontal shifting left or right? And so you guys can look right here for that. We didn't have anything being added or subtracted to our original starting point of where x is, so we have no phase shift. Okay. Is that okay with everybody? Are you okay that we're going to let this kind of sink in into